Here we have the infinite series of natural log of 1 plus 1 over n. And we want to show that this series diverges. And so notice that 1 plus 1 over n, 1 is the same as n over n. We want to get a common denominator here. So 1 is the same as n over n. And so we end up with n plus 1 over n. And the natural log of n plus 1 over n can be rewritten as n as the natural log of n plus 1 minus the natural log of n. So natural log of n plus 1 is the same as natural log of n plus 1 minus the natural log of n. And so let's get the sequence of partial sums and recall that s of 1 is the sum of the first term, s of 2 is the sum of the first two terms, s of 3 is the sum of the first three terms, and so on. And then s of k is the sum of the first k terms. And so s of k would be the sum of the first k terms. And therefore we allow k to run to infinity, and then the limit of s of k as k runs to k approaches infinity is the series itself. And so for this particular series, the first 10 terms, this is the first 10 terms. And so when n is 1, we get 2 here, and then we get 1 here. When n is 2, we get 3 here, and then we get 2 here. And then when n is 10, we get 11 here, and we get 10 here, and so on. And so the sum of the first 10 terms is about 2.3978. And then the sum of the first 100 terms is about 4.6151. And the sum of the first 1,000 terms is about 6.9. And the sum of the first 10,000 terms is about 9.2. And the sum of the first 100,000 terms is about 11.51. And so it looks like as n gets larger and larger, the sequence of partial sums also gets larger and larger. And so from here it looks like as n runs to infinity, then the sequence of partial sum also runs to infinity. But this is just by looking at this pattern right here. But now let's go find the sum of the first k terms, and then we can show that the sequence of partial sum does approach infinity. And so here's the sum of the first k terms. So this is the first term, this is the second, this is the third, this is the fourth, and then the last one is the kth term. Kth term. And so what it means is that in the place of n, we just put k. So n here we put k and k. And then the term before the kth term is the k minus 1 term. And so in the place of n, we have k minus 1, k minus 1. And then before that is the k minus 2 term. So in the place of n, we have k minus 2, k minus 2. And then before that is the k minus 3 term. And so in the place of n, we have k minus 3, k minus 3. And then now let's simplify a little bit. 1 plus 1 is just 2. 1 plus 2 is 3. And then this will become 4. This will become 5. And then 1 plus k minus 2, that would be k minus 2. 1 plus k minus 2 would be k minus 1. 1 plus k minus 1 would be just k. And then the rest we can just leave it alone. And then now we can see that this ln2, or the natural log of 2, and minus natural log of 2, that would be 0. And then the ln natural log of 3 minus natural log of 3. And then natural log of 4 minus natural log of 4. And then if we go to the next term, this will also get cancelled out. And then down here, we get the k minus 1, ln of k minus 1. It will cancel out with this ln of k minus 1, and then this k minus 2, ln of k minus 2. And then this will be ln of k, and then minus ln of k. And then eventually, this will cancel out with the term before it. And so the only thing that's left is negative ln of 1 and ln of 1 plus k. So the sum of the first k terms is negative ln of 1 plus ln of 1 plus k. And so that's what we have right here. The sum of the first k terms is negative ln of 1 plus ln of 1 plus k. But ln of 1 is 0. Natural log of 1 is 0. And so we only get natural log of 1 plus k. This infinite series here is the same as the limit of the limit of s of k as k runs to infinity. S of k as k approaches infinity is the infinite series. But s of k is ln of 1 plus k. And so as k approaches infinity, ln of 1 plus ln of 1 plus k will run to infinity. And therefore this sum right here approaches infinity. And it diverges. And so we have just shown that this infinite series right here equals to infinity, and therefore the series diverges.